Hi, my name is Harsha, and today I am going to talk about my literature survey topic Silicon Photonics on chip network architecture. Development in computer industry has been taking since 50 years ago at an unprecedented rate. Transistor technology has rapidly evolved, enabling the computers to make operations at exaflops. Supporting in chip infrastructure was unable to catch the pace of the transistor industry. One component in this is the on-chip interconnect network. Let us know a little bit about on-chip interconnect network. The first generation was buses. These were used for reading writing data from and to DRAM memory. Companies used to have custom bus interconnect intellectual properties. First industry standard came in 1996 and it was called ARM's Advanced Microcontroller Bus Architecture ABMA. Though it was late, it started an interoperability of IP core. Second generation. These are crossbars. Multiple cores started coming within a chip. Multiple requests at the same time created bottleneck and then bus interconnect failed. A new technology was needed. Crossbars was the answer. Advantages of crossbar is that source and target communicate simultaneously. This decreased the bottleneck drastically. As the chip complexity grew, crossbars needed a greater number of multiplexers and bridges to support the system. During 2000s, components became distributed over the chip, which made crossbar routing and connecting almost impossible. Third generation network on chips. Messages were made into packets and were transported across the chip to the destination. It follows OSA ISO model of communication. It follows topologies like mesh, point to point, and even indirect topologies like cluster based hybrid topology. It consists of process elements, network interface, switch, and routers. Failing due to the physical limitation of electrical wires and increasing complexity of CMPs made us to look for other alternatives, and the alternate viable solution was silicon photonics. Silicon photonics uses light as source instead of electricity to make communications. It has four main components: gateway interface, source, photodetectors, and waveguides. There are also auxiliary components including couplers, amplifiers, and modulators. Photonic network on chip is possible due to the manufacturing technique of CMOS industries. Let us talk about lasers. These are the source for photonic network on chips. Electrical signals from processor elements are converted into optical by modulating the light from lasers with the help of optical modulators. Example for one such of these things is microring resonator. There are two types of configuration based on the placement of laser, on chip and off chip. Lasers like germanium on silicon and 3 to 5 periodic based element based silicon lasers are examples of on chip lasers. Waveguides and optic resonators. Different type of waveguides are used to transmit different modes of light and different wavelengths of light. Same waveguides can carry multiple wavelengths at once using the technique called wavelength division multiplexing. Optical resonators are a special type of waveguides. These can be used as couplers and filters. The video here is an example of optical waveguides acting as couplers. Photodetectors. These are used to detect the modulated light and convert it back into electrical signals. Some of these have a disadvantage of having high dark current. Dark current is the current generated by the photodiode in absence of light. Newer materials are used to overcome this obstacle. 3 to 5 photodetectors and indium gallium arsenide INGAS photodetectors are widely used in PNOX. Literature survey. Of all the papers I've surveyed, these seem to be important, and some of them I'm going to discuss. A. Shaman and others discuss about an architecture for photonic network on chip, which use hybrid design combining an optical network for long distance communication and an electrical network for the small range communication inside the chip. The other one is Ascent Shasham and others simulating the hybrid photonic network on chip and a reference electric network on chip. In order to compare the benefits, nearly 17.6 power reduction is observed, which shows the level of efficiency PNOX can deliver. Sai Vinith Reddy and others realized the need for suppressing crosstalk in PNOX and suggested wavelength spacing and This has helped them increase the worst case scenario signal to noise ratio to up to 51.7%. Carty and others proposed an optical multi-level signaling, a method to double the bandwidth and few modifications, and assuming 128 wavelengths can be used for transmissions over the waveguide, and the ring modulate at 10 GHz with 4 to 5 THz free spectral range, a single OMLS link can achieve a maximum bandwidth of 2.5 terabytes per second, in contrast to the conventional link having only 1.28 terabytes per second. Learning curve. Out of uh, Out of doing this assignment, I've learned that network on chips and silicon photonics, when come together, can create high performance systems with very low energy requirements. Wrapping up, I would like to say that silicon photonics is one of the disruptive technologies that have been found during the recent 2 years. It has the capacity to take the in-chip communication to the next level, and this survey shows how the research around this field is already solving the problems of bandwidth and power effectively. Future scope of this work can concentrate on how silicon photonics can help in using data center application specific integrated circuits and in latest applications like machine learning and deep learning. Thank you.